Okay, today we're going to come up with an interesting technique for calculating the area of a region that is unbounded. So I'd like you to take a look at what I have graphed here in purple, that shaded region. Under the graph, y equals 1 over x squared, starting at 1, and we're going to go forever to the right. So we're not stopping, and we're going to attempt to calculate this area. If we can come up with a fixed area, we call this a convergent area, our convergent function. If we cannot calculate it, then we refer to this as a divergent value. So let's take a look at this. Convergent or divergent. So the basic question is, I have an infinite amount of fence to make my graph. Is my area fixed? So first thing is, I'm going to set up my basic integral as, let me put it here. I'm going to take the integral from 1 to infinity of 1 over x squared dx. Now, what I'm going to use is this idea here. Sorry, my cat. Need a more expensive computer next time. Okay, so what I'm going to do here is redefine this as a limit from t approaching infinity, and now I'm going to integrate it from 1 to t, and it's still going to be 1 over x squared dx. So basically, notice I took out the infinity and I replaced it with a t, because now I'm describing this as a limit. So t is going to change values all the way till I approach infinity. So now I'm going to take the antiderivative, still have my limit as t approaches infinity. The antiderivative of 1 over x squared is negative 1 over x. And again, I'm still evaluating that from 1 to t. Okay, so first thing I'm going to do is plug in my t. So I'm going to have negative 1 over t minus a negative 1 over 1 when I do my substitution. Now, I'll split this up. Well, first of all, let's just take a look at this here. You should reckon, I'll go ahead and rewrite it. Negative limit as t approaches infinity of 1 over t plus the limit as t approaches infinity of a constant. Clearly, this is 1. Let's take a look at this. We've examined this before. So 1 divided by t, as t gets larger and larger, 1 divided by a bigger and bigger number, you should recognize this as one of the fundamental limits that goes to 0. So my final answer is 1. So I was able to calculate the area under this curve, 1 over x squared, from 1 to forever to the right. Forever, unbounded. And I got a fixed value. And so I'm going to write that as my final answer. So from 1 to infinity of 1 over x squared dx, final answer is 1. This is called convergent. Pen, please stop doing that. If I would not have gotten a fixed value, if I would have gotten positive infinity or negative infinity, or well, it would have to be positive infinity, but had I gotten a positive infinity, we would have called that answer divergent. So again, this is a type 1, and if you refer to your book, you will find the definition for an improper integral of type 1. So let's just kind of look at what we're doing here, what I did. I did this a version of type 1, and I started at a fixed value a, and I went to the right forever, and I redefined my area, that infinity, as a limit as t approaches infinity. Okay, and again, this is just going to the right. If we had the exact same setup going to the left, that would be part B of type 1. So either to the right or the left from a fixed location. Only thing is, if you're using the digital book, I'm just going to tell you it's got a little typo. I've already notified the publisher. This is a negative infinity, and this is a negative infinity. The book actually shows it as a without the negative sign, so be careful with that. But it's basically, I'm just replacing this negative infinity, so I'm taking the limit as t goes to the left and replacing infinity, negative infinity with the t. Okay, again, if the limit exists, it's called convergent. If the limit does not exist, divergent. That's it. Okay, so this is type 1. Now, I'm going to erase this, and we're going to talk about type 2. And again, same idea that we're dealing with here is that I'm dealing with a region that is not bounded, but I may or may not be able to calculate the area under that curve. So we're going to talk about here right now type 2. And that's this region over here. If I was to shade all of this, and let me shade it in as quickly as I can. Okay, so type 2. Why is this region also not bounded? So what I'm going to be looking at here is the region from 0 to 1. Now, what's interesting about this is as x approaches 0, this function keeps going up and up and up and up and up and up and up. It's got a vertical asymptote at x equals 0. So in this question, I have to ask myself, is my function continuous, and can I find the antiderivative from 0 to 1? So I need to be continuous from 0 to 1, not including 0. And this function is. So because it is, I'm going to, again, redefine this region using a limit. And let's talk about what the trouble area is. This is my trouble area. So that's what I'm going to redefine as the limit. Stop, please, pen. So that's going to be the limit as t approaches 0. And on this, I'm approaching from the right. In other words, only positive values as I approach 0. And again, I'm going to take my integral and I'm replacing that 0 with t to 1 of 1 over x squared dx. So now, again, the real question is can I find this value? So we go through the process, take the antiderivative, still have t approaching 0 from the right, and I'm going to now have negative 1 over x from t to 1. And again, I'm going to plug in. Sorry, getting ahead of myself. As t approaches 0 from the right, and I'm going to plug in the, yes, negative 1, or plug in the 1, so I'm going to have negative 1 over 1 minus a negative, so positive, 1 over t. Okay, so now the real question is can I find this value? And in this situation, I cannot. So this clearly is negative 1 plus the limit as t goes to 0 from the right of 1 over t, and 1 over t as t approaches 0 is actually this is approaching positive infinity. So this region is called divergent because we could not find a fixed value. Basically, the area for region 2 is infinity, but the area for region 1 we found earlier, I already forgot what it was it 1? But whatever the area was, we found it, so this is convergent, region 1, region 2 is divergent. I'm going to post a couple more examples.